okay, on a curved surface. Now if you are in a plane, let's say on a two-dimensional plane, what is the distance, what is the shortest possible distance between the 2 points? It's a straight line. Clear? So I can say a geodesic uh, roughly in a plane is a straight line. Geodesic means the shortest path between 2 points on a general curved surface. That can be a flat space, that can be any curved space. Got it? Okay, so let's say you move on a surface of the sphere, you move from one point to the another point. So what is the shortest path that you can take in moving from one point to the another point on the surface of the sphere? So that shortest path we call as a geodesic. Okay, because the surface of the sphere is genuinely curved. समझ आओ? Okay, so let's recap. Okay, so let's try to figure out the geodesic equation. Or in other words, I will say let's figure out the equation of motion for a particle. For a massive particle. Before doing that, we will recap the equation of motion for a particle in special theory of relativity. Okay, from the action principle. Okay, so in SR, okay, special relativity, we write action this way. So action is m, okay, integral ds. Okay, ds is the line element, or you can use any kind of parameter here. Is that true? This is the action. C is equal to 1 here. It's actually mc ds. C is equal to 1. Okay, so now let's write it. So what is the action? So it is like this in m. Okay, ds is anybody? So it is root of, so minus eta ab dxa dxb. Clear? This is how we write it. It is like this thing. So you are having ds square is equal to eta ab dxa dxb. Samajh? You got my point? Okay. So why I have taken this minus here? Because the determinant of this eta is what? Negative. It's what is eta ab? So yesterday I have talked about this thing. So it is diagonal minus 1 plus 1 plus 1 and plus 1. Clear? Got it? Samajh aaya? So now let's rewrite. Okay, so let's make the variation of the action. So you are having delta A is equal to 0, gives you the trajectory of the particle. Is that true? So now tell me where this particle is. This particle is on the background. I mean, the geometry is flat space-time. In that flat space-time, this particle is moving. You are looking only the dynamics of that particle in that flat space-time. Clear? Samajh? And there is no interaction of this particle with respect to the other fields. Samajh? It is simply a free particle moving on a surface. Samajh? Moving in a flat space-time. Now let me vary the action. Delta is equal to 0. How to do that? Okay, so we need to vary this action. So I can write this action as, okay, so before doing that, so I can write this object as minus m integral of minus root ab. So because this integral is invariant of any parameter transformation. Okay, you can take any kind of arbitrary parameter. Okay, so because our curves are what? Parameter invariant. You can choose a parameter. Samajh? You can make a transformation of a given parameter. You can put it as a lambda, dx lambda, and make a transformation. This there is a parameter invariance in this very action. This we have done earlier as well. Okay, so I can put it like this thing: dxa by d tau, dxb by d tau. Okay, and then you can write d tau outside like this thing. So that means it's minus m eta minus eta ab. So this you can write like this thing: x dot a, x dot b. Okay, so these things we have already done. So let's make a variation of this action. Okay, so let me write this variation of action is equal to 0. For that matter, so when I take variation of action equal to 0, I need to vary this ds, is it? So let me vary it. So I can write this thing, variation of ds. So let me vary this thing. What is our ds? Just tell me what is our ds? It is variation of this root of, so I am, okay, doing it just for you people, or otherwise we have done this thing already. Okay, so can I write it? Now tell me, it is root of, you can think it as a root of x, so it is simply 1 divided by twice root of minus eta ab dxa dxb. Can I write it? Then you have to vary minus eta ab dxa, differentiation inside the function. Okay. Clear? So now what this is equal to 1 divided by twice ds. Okay, this eta is a constant, so it will come out. So it's like this thing, minus eta ab. Then you are having differentiation of, so let me write it as dxa dxb. So if you see, this is essentially actual dx square. Teacher, this is dx square. What is the differentiation of dx square? Twice dx. So this object I can put like this thing, 2 dxa, then variation of one of the dx's, dxb. So this object is like this thing. So that is equal to twice dxa b of delta x. Everybody? Okay. So now let's rewrite it. So therefore, this variation in s, so that's equal to, okay, so you are having minus eta ab. So this 2 and that 2 cancels out. So it is 1 by, let me write ds. So let me write it this way, minus eta ab, okay, dxa d of variation of this x by what? ds. Clear? Can I write it? So now this you can write as, so you raise and loud in this is, so it will be something minus dxa d of delta x a by ds. Samajh aa? Can I write it? Okay. So this is our variation. Okay, now what is this dxa by ds? That is 4 velocity vectors. Samajh aa? So now let's write, therefore I can write this variation in a, so that's equal to minus m, variation in ds, so that's equal to minus m. Okay, so what is this variation? So minus and minus becomes plus, so it is dxa d of delta xa by ds. Okay, so you can write, okay, so now integrate it by parts. So to free this very delta x within this differential, okay, so let me write it first. So it is integral ua, okay, d delta x. So I can write it like this thing, ds. So what is ua? Ua is simply the velocity vector. This is how we define the velocity. ds and d tau has the same meaning. So what is ds in terms of d tau? It is c times d tau. D tau is actually ds by c. Since we are in c equal to 1, so you can replace them. There is no problem. Okay, so I can replace this ds by d tau. There is no problem, essentially. Okay? Okay, so now let's integrate this by parts. So this I can write m ua. So when you integrate this by parts, so it will be something delta xa defined at where? Some endpoints. Endpoints of the trajectory. Okay, then minus integral, so differentiation of u, so it is dua by ds, you can say. Now okay, so let me write d tau. So let me write d tau. So shall we put s? Okay, let's write s. Let's write s. Okay. So let's write this. So it is du ds. So what is the another thing? So when you integrate, so it is simply delta xa. Clear? So much what is here? Ds. Okay? Any problem? Okay. So now this very term, since the variation at endpoints is equal to 0. So variation at endpoints is equal to 0. Okay, so and this has to be equal to 0. Clear? So now this is actually a free variable. So these things are linearly independent. It means this object has to be equal to 0. So this is the equation of motion for a free particle. So that means free particle travels with actually a constant velocity. So it's something dua by ds that's equal to 0. Or in other words, I can write like this thing. In terms of the proper time, dua by d tau that's equal to 0. So that means in one frame of reference, so if you try to figure out the equation of motion of a free particle, so that is this thing. So it implies your velocity is what? The 4 velocity vector of the free particle is what? A constant. It means if you are having a free particle, it will always move with a constant 4 velocity. So, you got my point? That's true, huh? Okay. So now let's check. Okay. So because our laws of physics should be invariant under a coordinate transformation, is it? So that means if I am having this kind of object in one frame of reference, it should hold where? In the another frame of reference. If I make an arbitrary, okay. If I make a Lorentz transformation, this is okay. There is no problem, huh? So much, but if I make an arbitrary coordinate transformation, I need to check whether this equation is an invariant or not. Okay, so for that matter, what I will do, so let me write this thing, this du by d tau, so I can put it like this thing, okay, in terms of the coordinates. So I can write it, let's see, dxb by d tau and dua by partial x d, dxb by d tau and partial ua by partial x. Can I write it? Just the chain rule, huh? So it is in the same coordinates because x is depend on the parameter tau, huh? So much x is define your coordinate trajectory, huh? Okay. So what this object and this is equal to 0 actually. Okay. So what this object is? So it's actually the velocity vector. dx by dt is a velocity vector, clear? Okay, so I can write this thing. So this is something ub. Now this is something partial b and ua. That's equal to 0. Now this is a velocity vector. Velocity vector, it's a 4 vector, clear? That means under Lorentz transformation, it will under a coordinate transformation, it will transform as a 4 vector. So look at the principle of the relativity. What it requires, or the principle of general covariance. It requires your equation must have a tensorial form. That means if you are having a quantity defined in one frame of reference, it retains its properties in the another frame of reference. You are having the same physics in the another frame of reference. Now here what you are having, so we are trying to actually check that kind of object here. So this ub is a 4 vector, is it? So that means when you make a transformation, it will be a 4 vector. Okay, so is this okay? So this is in. We need to figure out what is the transformation rule for this object. Or in other words, if you look at this thing, this complete object, it's actually it seems to be a 4 vector. Does it seem? Why? Because there is only one free index. So this is actually a quantity which is having only. Look at this equation. You are having only one index, is it? So it looks like it has to be a 4 vector, clear? But we need to be careful in checking it, whether it is really a 4 vector or not, or whether it's really a tensor equation or not. Let's check it. Okay, so let's look at this. Okay, so you are having this ub, so it's a 4 vector, clear? Because it's a velocity vector. Okay, velocity is a 4 vector. Clear? So this we have already seen. The tangent vector turns out to be the velocity vector when the particle describes a trajectory. Clear? Samajh? Okay, so when you are having, now let's look at this object. What is the property of this object? So you are having a partial derivative of a 4 vector, and this we have seen it is not a vector. It's not a tensor quantity. This we have seen yesterday. Clear? So this I have shown you yesterday. The first derivative of what? Partial derivative of a tangent vector is not what? A tensor, or it does not transform as a tensor. But in case of the special theory of relativity, it's a tensor. So that's why it holds in all frames of inertial frames of reference. But it means since this is not a tensor, this object is not a tensor. Or in other words, this object is not a tensor, okay, under a general coordinate transformation. It means this equation under a general coordinate transformation, this equation will not hold in any other frame of reference. Samajh aaya? Now the question is why there is a problem. Okay, why it does not hold? Simple reason is that we started with a metric that is actually constant in coordinates. That was a constant matrix, eta AB, is it? Samajh aaya? Because that does not count any curvature of the underlying space-time. Samajh aaya? So when it does not cover any kind of curvature, so the equation of motion that will turn out, okay, equation of motion what you derive from that will not be actually in general and independent, an invariant equation. Samajh aaya? Clear? So now what we do, we generalize that action. Okay? So we generalize action to now the curved space like this thing. Root of minus GAB, that's now dependent on x. So dxa dx. Clear? Samajh? Now this way, okay, you can make now around a given, if you take an event around that, in the infinitesimal region of that event, you can actually reduce it to the inertial coordinate. So that I have told you in the last lecture how to do that. To put the first derivative is equal to 0. Okay, locally you can make it to be inertial, but globally you can't do it. Okay. So any question till now? Okay. So this I can write as like this. So this is simply your minus m d tau. Okay, d tau is same as ds square. Samajh aaya? I will use d tau here, proper time. Clear? So this is our. So now what is our d tau square? Anybody? What is d tau square? Minus GAB dxa dx. Clear? So now let's vary because we need to vary the action. Okay. So let's take the variation of this d tau square. It's equal to minus, so it is actually a variation of this GAB dxa dx. Clear? Okay. So this I can write as, so this object I can write like this. So it is twice delta tau and vary twice d tau delta d tau. Sure? So that's good. Now let's make a variation. So it's minus. So the variation of GAB, and keep these two as such. Okay. So minus, this minus is here. So you are having GAB, then the variation of dxa dx. Okay. Clear? So now I can write this variation. Okay, so let's take this variation. This delta GAB. Okay, let's use the chain rule or the Euler's theorem. What is the variation of f? It's partial f by partial x. Let's say, okay, multiplied by dx. Teacher, so how I can write it? So something partial by partial xl. Okay, some GAB then what should I put? Yes. Variation in x. It is the variation with respect to x. Clear? So this I write as partial L GAB. Okay. So now what about this thing? This objective. So this is twice dxa. Okay, delta dx. Can I write it? So this I can write twice dxa d of delta. समझ आवा? So now let's write therefore this variation in tau. So this variation in d tau, that's equal to half of. Okay. Okay. So let me write d first. So twice d tau, variation in tau, that's equal to, you are having minus. Okay. What is this variation? So let's put the okay, so let's put this one. So what it is? Minus partial L GAB and okay, delta of XL, then you are having DXA DXB, then you are having minus, okay, twice DX, okay, GAB DXA D of delta X. Clear? Huh? Any problem? So you can, I am just going slowly for you people. Okay. So you can take minus out. So it is minus 1 by 2. Okay. Okay. So I will divide by d tau. So it is partial L GAB delta XL. Okay. DXA DXB. Okay, so I will divide by, okay, so this tau I am dividing, clear? So I will, that is here. So on this area I will write one more d tau and multiply it by what? D tau. समझ आवा? Okay, then you are having plus GAB, okay, so twice, so it is twice GAB DXA by d tau, so d, okay, so this d tau comes here. Then for this very term, I will put a d tau term like this thing, then multiply by d tau. समझ आवा? Everybody? So this is our variation in tau. Let's substitute where? In the variation of the action. Okay? Everybody followed it? What I have done? Huh? Okay. Yes? Huh? So now let's write. So therefore variation in action. So the minus m, and you are having there minus half, clear? So this will make it plus. So then I am having within the integration. So let me take half with the first term. So you are having half. Okay. Then you are having this partial L GAB variation in XL. Okay. So let me write it this way. So what this object is? dxa by d tau. This is UA. Is that true? What this object is? It is UB. So the velocity vectors. So I will write it like this: UA, UB. Clear? Okay. So what is multiplying them? So the multiplication is delta XL then d tau. Okay. So what is the next term? So 2 and half cancels. So it is GAB then you are having dxa by d tau, that's actually ua, then you are having d by d tau, variation in this xb, then you are having this d tau. समझ आवा? Okay, now in order to simplify this thing, you are having this actually differentiation of what? This small element, this element, delta xb. So I want to make now integration by parts to get rid of this independent variable. समझ आवा? Clear? Okay. So let's say integrate by parts, second term. Second term. So let me write it separately. Then okay. So what is that? So you are having integration GAB UA d of delta xb by d tau, then you are having d tau. So let's integrate it by parts. The first term will be, okay, so these are actually the first term and this is the second term. So first term is like this thing. Keep first term as such, integration of the second term. So it will be simply delta xb evaluated at endpoints. Okay. So this is the element because you are integrating on this very part. So this object is evaluated where? At the endpoints. समझ आवा? So then you are having minus integration, differentiation of the first. So it is d by d tau of GAB UA. Clear? Okay, integration of the second. So that will be simply delta xb beta. समझ आवा? So this goes to 0 at endpoints because the variation at endpoints is fixed. Okay, so endpoints are fixed, there is no variation at endpoints. Clear? So now let's substitute it back in that equation. Okay, so it means I will write this equation as like, so you are having, okay, so the first term goes, so it's minus d by d tau, okay, GAB UA, then you are having this delta xb d tau. Okay, now look here, you are having L is a dummy variable, isn't this? Okay, so this contains this delta x delta tau, this d tau, this also contains delta x d tau. Here L is a dummy variable, here B is a dummy variable. You can use for this B same as what? L, because these terms are in the addition. समझ आवा? Clear? So this term I can write this very term. So let me write it this way. So I can write it as d by d tau of GAL UA, okay, then delta XL beta. So you can take this out. So this has to be equal to 0. समझ आवा? Okay. So what it means, so when this is equal to 0, so it means like this thing. So d by d tau of the GAL, clear, UA, समझ आवा? That's equal to half of partial L GAB, okay, UA. Okay, now look here. So this again the velocity vector on this very side. So much, and this is the differentiation of what? So that means the motion on a general curved surface is driven by the derivatives of the metric tensor. So much, metric tensor defines your curvature at okay at certain level. So much, so let's say if metric tensor is independent of the coordinate, then it is equal to 0. You have written your own equation, what was where? In the flat space time. Now your equation of motion, or in other words, the velocity of the free particle is governed by where? By the derivatives of this very metric tensor. समझ आवा? Clear? The motion of a particle on a curved surface is governed by the derivatives of this metric tensor. Let's put it in a more beautiful form. Okay, so let me use, okay, so since I have already used this A here, so let me use here as, okay, so let me write like this thing. So we are having this equation which we are trying to write it in a beautiful fashion. So UA, so that's equal to half of partial L G, let's write IJ, okay, UI, okay, so that you don't get confused with the indices. Okay, so what is the free index? L. So your free index is L here, all of the demi variables. Clear? So now let's put it in a more beautiful fashion. So let's take this very term. So you are having RHS, so that's equal to d by d tau of GAL UA. Okay, so let's differentiate it. So it will be GAL DUA by d tau. Why you can't take this here? Because this is dependent on the coordinates. So there will be, because of the coordinate dependence, so you need to take the derivative. Derivative will not be 0. Okay, so it will like this DGAB by d tau. Clear? Okay, so this I can write as GAL DUA by d tau. So plus, so okay, since this has a coordinate dependence, clear? So I can write it like this. Let me write partial, okay, some xb by dxb by d tau, okay, partial gab by partial xb. Can I write it? Simple the chain rule. Huh? Okay. So what this object is? So this object is your velocity vector, right? So this is equal to GAL DUA by d tau. Okay, plus let me write this thing first. So it is partial D GAB. So this will be UB. Samajh aa? Got it? So this is your UB. Any problem? Any problem till now? Clear? Okay. So this is actually a mathematical derivation. Think we have started doing mathematics now. Huh? Okay, but I will simplify many things. Huh? Okay. So let's look at this very term again. Okay. Can anybody tell me what is there in this very term? Can anybody guess what exists in this very term? Look here. So you are having this GAB, it's a symmetric tensor. Is it? Is it true? Gadwad Maga? Oh no, there is a Gadwad. You are having, this is not B, this is L. Nalaiko. So you can't be having 3 indices same. This is AL. I hope not. It's a huge mistake. Samajh aa? Now look here, this object is, so that's why we start with a mistake. So this object is this UBUA, it's a symmetric tensor, is it? First tell me, is it symmetric in indices A and B? So what it means? So what? Okay, so let's, so you are having this product UA, UB is the same as UB, UA. Samajh aa? So that means under interchange of A and B, it is same. So it is symmetric. When this object is symmetric, it means this must be what? Symmetric in the indices B and A. Got it? So it means, okay, since this is, okay, so let me write for you people. UA, UB is symmetric under interchange of A and B implies this partial B, GAL must be symmetric. Must be symmetric under AB exchange. Okay, so that means I need to symmetrize it. So we need to symmetrize it. So what it means? So therefore our RHS is equal to GAL dUA by d tau, okay, plus, so this I can write half this GB, okay, so this I can write like this thing, partial B GAL plus partial A GBL. So this is the symmetrization, is it? So BA plus AB, Isha. So you keep this as UA, okay, clear? Okay, so now let's use it here. So, okay, so this is equal to LHS. So therefore, we write like this thing. So this is equal to LHS. This is equal to, what is LHS? This sir. समझ आओ? Huh? Okay. Can I write it like this thing? GAL dUA by d tau, okay, plus, okay, so let me write for you people. Again this step, partial B GAL plus partial A GBL. So instead of AB, I will write IJ here. So because they are the dummy variables, B is summed and A is also summed, it's a dummy variable. Let me write for B as partial I GJL, okay, plus partial J GIL, like this thing, IJ. So that's equal to UI UG. Clear? So this is equal to half of partial L GIG UI. समझ आओ? Just I have replaced A and B by what? I and J. So this term is same as this. There is no problem. Okay? Clear? Okay, so now we can write it. So which implies, so we are having this equation, GAL dUA by d tau. So that's equal to, take this on the other side. So it is half of, like this thing. So partial L GIJ minus partial, okay, I GJL minus partial J GIL, okay, UI. So we call this as the geodesic equation. Okay, geodesic. Oh, so we will simplify it in a moment. Okay. So this is an equation of motion of a free particle on a curved surface, or the curved surface space-time. समझ आओ? Have you written it? So let me simplify it. So look here, you are having G on this very side, is it? समझ आओ? So what I want to do, I want to take this G on this side. So that means I have to multiply it by G. It's inverse. If I multiply by G inverse, this will be identity and G inverse will come here. So let me use this identity. Let's say GAB, okay, GAL. So what is that equal to? Delta BL. So let's use this identity. That means I will multiply this by GAB. So it implies I will use GAB, GAL. D must use both. So it is DUA, right? D tau. So that is half of GAB. And now like, why should I use? Oh. Well, A is already a dummy variable here. You are having G, okay. So GAL is already here. This A is a summed over index. So you write it by, let's say GBL. So what is that equal to? Delta BA. Why? Because this A is already summed. You cannot sum it again. You cannot contract it again. So I am contracting this index, this L index. So समझ आओ? So you are having now GBL GAL DUA by D tau. Okay, does it make sense now? Does it make sense? So use your A is contract, L is contract. समझ आओ? So that's equal to half of GBL. Okay. So then you are having partial L Gij. I will tell you in a moment. There is a nice way to remember it. This equation. You don't need to worry. Partial I GJL minus partial J I UI. Okay. So now what this object is? Delta B. So when you sum over A, this A will be replaced by B. This is a delta function. Okay, so that means this A will be replaced by B. So it implies your equation of motion. It is dUB by d tau. So that is half of. Okay, so let me write. Okay, forget about everything. So how many indices are there? L is a contracted index, is it? So in this very thing, you are having B, I, J, which are free indices, is it? So forget about UI, UJ. So I will write it in this way. So let me write it as. So there should have been a minus sign. There is a minus error somewhere. There is a minus error. Do you think so? There is a minus error? There is a minus error. So somewhere the minus in front of this side is missing. Somewhere. Somewhere the minus sign that was sitting in front of this left hand side is missing. Yes, I will tell you where. Can anyone tell me? When we do the integration by parts, so minus sign we have forgot somewhere. Just please correct it. So, okay, so let me write it this way. So let me define a quantity. Okay, so let me define a quantity which is very useful quantity. Okay, forget about this thing. So there is a minus sign somewhere. Just check this sign. Okay, so you have to be very careful. So let me define a quantity like this thing. So look at this very object. Now tell me which index is an upper index in this very quantity. You are in BL, is it? But L is an index which is contracted, clear? Yes, so there is a contraction over L, that means you don't need to worry about this L. So therefore in this very quantity only the index B remains. So let me write a quantity this gamma, put an index B here, okay? So what are the indices which are free in the bottom, at the bottom? Are the covariant indices. So it is I and J. So let me write this I and J. So I have defined a quantity gamma carrying three indices, okay? So one is at the top, another two are at the bottom. So how is it? So now let me give a way how to write these things. So what you do, if you are an index, whatever you are an index here, you will write first G. So put this index first, clear? Then put a one contracted index. So let's call the contracted index is L. So here, then you write the partial derivative with respect to this L. Then you write a G metric tensor which carries these two indices at the bottom. Then you write a minus sign, okay? Then make a cyclic ordering. So what is the cyclic ordering? Then I will come here. You write I, G, J, L. Then you write minus, take J here, so it is G, L, I. Because, okay, so it is G, I, L and G, L, I are same, because G is a symmetric tensor. So this is a way to write. We call these as the Christoffel symbols. Okay? Or affine connection is a. So remember the term affine connections. Usually people call them Christoffel symbols of the second kind. but let's call them only the Christoffel symbols. So, समझ आओ? You can bring down this B at the bottom. There is no problem. Huh? So that means without the G, so whatever is here in here, so you write as what? GLIJ. So, समझ आओ? तो यहाँ का समझ. So in other words, if I write like this thing, gamma Lij, so what is that equal to? Half of partial L Gij minus partial I GJL minus partial J GLI. Clear? So we call these as the Christoffel symbols of first kind. This is known as Christoffel symbol of second kind. What is the relation between this and this? So you are having this object as this gamma and this entire object as containing G. So it means this gamma B Ij is equal to G B L like this. Although it carries three indices, but it is not a tensor. Okay? So it looks like a tensor, is it? But it does not have this tensorial properties. It does not transform as a tensor. Only the product of this multiplied by this object transforms as a tensor. So let's write the geodesic equation now. So we write geodesic equation as du, let me write d by d tau plus, yes, this gamma b I j u I u j. That's equal to 0. So these are what? So this is our geodesic equation. So it is the generalization of what? The equation of motion in presence of, let's say, the potential phi, the Newton's equation of motion. Okay. So समझ. So it is the generalization is this. We will see in the weak gravitational field limit this reduced to the equation of motion. Okay. So that we will also carry. First we will look at this Christoffel. So what is known as geodesic equation? More precisely, it is known as metric geodesic equation. Yeah? Okay. But forget this. We will study only this kind of equation. Okay. So now let's look at this this Christoffel symbol. Yes. Any problem? Huh? Okay. So let's look at this. Now you know this Gij. It's actually a symmetric tensor. Clear? So this gamma, this Christoffel symbol or the affine connection, they are actually symmetric under the interchange of these covariant indices. So what I mean by that, let's check it. So if I am having this gamma Ij, let's say this is K, so it is same as gamma K Ji. So it's symmetric under interchange of what? These two indices. समझ आओ? तो यहाँ क्या समझ? Let's say I want you to know that how many components this gamma is having. Okay, so let's forget about its symmetry properties. You are having I, J, and K. These are the three indices. Clear? Let's say each index goes from 1 to n. That means it carries n components. So how many components it will be having? Tell me. How? N into n into n. That means n cube components it is having. Let's say if you are having in the 4-dimensional space, 4 space time. So how many components you are having? 4 into 4 into 4. So that means 64 components. If we don't have the symmetry properties here, but it is symmetrical. Forget about this index. Okay, so first check whether it is symmetric or not. Let's interchange gamma Ij. This Gij is symmetric, is it? There is no problem. Now let's check I and J and I and J. So this term becomes this thing and this becomes this thing. So that means this is symmetrical. So okay. Now let's count in this very case. Forget about this top index. Okay. So you are having this as a symmetric matrix. Clear? How many components a symmetric matrix is having? So you are okay. Forget about this top index. So it is actually a square matrix then. So you are having, let's say, Aij, which is a square matrix. For example, how many components it will be having? N square. So if it is symmetric, how many are there? So you have to count only the from diagonal to the upper elements. Clear? One side of the diagonal. How many are there? 1 plus 2 plus up to n. Clear? So how many are there? N into n plus 1 by 2. समझ आओ? Okay. So that means this will be having n into n plus 1 by 2 elements. समझ आओ? So it means for every k value, how many you are having? So that means you, okay, so let's say k goes from, okay, so for each k we have n into n plus 1 by 2 components. So that means I have to count them how many times? N times, okay? So how many are then? N square into n plus 1 by 2. So that means you have to multiply it by n. Okay, so let's do it in a simple way for a 4-dimensional space-time. So in 4-dimensional space-time, okay, 4-dimensional space-time, okay, how many components will it have? 10, because it's a symmetric tensor. Symmetric tensor in I and J. For I and, okay, forget about this k. It will be having 10 elements, correct? So we'll be having, okay, for each k, we have 10 components. So how many k are there? So k is equal to 4. Let's see, because we are only where 4 space-time dimensions. Okay, so that means you will be having this gamma k I j has 4 into 10, that is 40 linearly independent components. So that means in 4-dimensional space-time, how many terms you have to evaluate? 40 terms. Now you can see the rise of these affine coefficients. But you will see in the most of the cases, many of these 40 terms turn out to be 0. Majority of the terms, only few terms remain. So let's take a simplest of the example, then I will stop. Let's take a simplest of the example. Next, yes? Equation. First we will try to figure out the affine coefficients in the simplest of the case. Then you will see. Okay, so let's take a 2-dimensional space. Okay, in spherical, I mean polar coordinates. So I am having polar coordinates r theta in 2-dimensional plane. What is our ds square? So I need to know the matrix. So it is dr square plus r square d5 square. Okay, in the polar coordinates. Sorry, or d theta square. R square. What is g? So what is gij? So it is equal to 1, 0, 0 r square. What is its inverse? Inverse means the upper one. So it's a diagonal matrix. Inverse of the diagonal matrix is the inverse of the diagonal elements. Now you can multiply the two, you will see it is equal to identity. Clear? Now what I need to figure out? These affine coefficients. Now look here. How many variables you are having? Only 2 variables. That means each index I, j and p, they go from r and theta. So that means only 2 components. So let me write like this. So that is the formula. First I will use this b as, let's say, r. Okay. So that is first component, and then I will write this as r. When I take this I and j, both I and j, I is equal to r, j is equal to r. Got it? Then I can take b, I will keep fixed. Then I will take I equal to r, j equal to theta, because these will take the different values. So let's do it. So what it will be? Like this thing. 1 by 2 g. Okay, b is equal to r. L is there. Because L is a dummy variable, there is a sum over L. Okay, partial L Gij. What is Ij? It's RR. Minus partial I, that's R, Gj, it is R, and L minus partial J, it's R, GL is there, it's equal to R. Okay? So now there is a sum over L, so you sum over L. What is the values of L it takes? R and theta. So only 2 values. So it's like this thing. 1 by 2 GRR, like this thing, partial R, GRR, minus partial R, GRR, minus partial R, GRR, plus another term, half. Okay, GR, now L will take value theta, partial theta GRR minus partial R GR theta minus partial R G theta. Clear? So you got the point? Now what is GR theta? This is R, this is GRR, this is GR theta. So that is equal to 0. So this object is equal to, so this object is equal to 0. So that means this term vanishes. Okay? Now what is GRR? So GRR is equal to 1. So I need to look at this thing. Now what is this GRR? This small g, RR down. So it is here. It is 1. So differentiation of 1 is 0. So what is GRR? It's 1. Differentiation of 1 is 0. Differentiation of 1 is 0. So what you are having therefore? Therefore this gamma R that's equal to. Got it? So what is the next term? So let's write. Next term is like this thing. GR. Now you have to write for this I. Let's keep I as R. J as theta. Clear? Then write. Okay. Keep R because how many possibilities are for the R? 4 possibilities. समझे R. So it is theta R. So write this thing. Then you are having R theta theta. समझा? Got it? Similarly now. Okay. So let me calculate this component. So these components will be equal to 0. So you have to show it. So this will be home assignment. So just substitute in this very formula and use that very metric. You will see these are equal to 0. So let's check it. I will do it myself. Then I will tell you the another 4. समझा? So what is our this thing? What is the next? GR theta theta. So it means it is theta theta. Okay. So it is theta theta. So it is theta theta theta. Clear? समझा? So what it will be? So it will be RR. So here it will be theta theta. Okay. Then you are having theta theta here. Then you are having this theta and this theta. Okay. Then you are having R. Sorry. Yes, R is here. R theta. So this is equal to theta theta. So this will be equal to theta. This will be equal to theta. And this will be equal to theta. And this is equal to theta. Have you got it? What I have done? Huh? तो यो समझ में क्या पर? अगर नहीं यो समझ के, just tell me. यो समझ? So I have simply what I have done. Since there is a sum over L, so L goes from R and theta. So I have put R. Okay. So here R and just the G theta will remain same. So then you are having partial theta. This L will become R. So you are having this L becoming R. Huh? So here it is theta theta. Now you are having R theta. So you are having this L will become theta because L goes from second term will be theta. G theta it will remain. This L will be theta like this. Now let's look at this. Okay. Again, what is this GR theta? This term is again 0. समझ? So that means this goes. Now what is the GRR? It is equal to 1. समझ? Now let's look at this thing. What is theta R? It is equal to 0. R theta is also equal to 0. So what remains? What is G theta theta? It's R square. So in this very term, so I'm having okay. So I'm having. So there is another way. This is a brute force method. What we say. There is another way to do it, a simpler way that I will take later on. So 1/2 GRR. Okay, partial R G theta theta. So this is only the non-zero term. So it is half of what is GRR? It's equal to 1. Sorry, it is partial R. It's partial R. So it is G. Okay, partial R. What is G theta theta? It's R square. So how much is that? Twice R. So it is half twice R. That's equal to R. So therefore this R theta theta is equal to. समझा? So now let's check. Okay, so other possibilities. Now here I have fixed R, is it? At the top index. Now I am having another possibility theta. So it is theta. So now again you start with what? I and J is RR. Okay. So you start with R theta. You start with theta R. You start with what? Theta. समझे? So let me write the values of these things. Okay. So this is equal to 0. This is equal to 1 by r. This will be also equal to 1 by r. Okay, you don't need to. If you know r theta, this you don't need to calculate. Why? It is symmetric. Is it? So it is 1 by r. So this will be equal to 0. Samajh aaya? Okay, so how many are now non-zero terms? Only 3. Okay, so you are having only 3 non-zero terms here. So out of how many? 8 terms. So samajh aaya? So you need to figure them out. Okay, so let's stop.